Okay, so today Ota will be giving a talk on the work he did over in Norway, and yeah, let's enjoy.
Okay, hi everyone. Thank you for introducing. My name is Ota. I study aerospace engineering in the University of the West of England. I'm a placement student currently with Artemis Group here at STFC, working on ultrafast lasers. And I'll tell you something about this project I took part in, which is organized by ESA Academy. The rocket we can see in the background is not how it, well, it is kind of how it ended up. We'll get to that. So first, what's ESA Academy? It's part of ESA Education Office, and they organize activities for university students. One of them being Fly a Rocket. Anyone from ESA member country can apply to their activities, from bachelor students, master students, PhD students. Some people do thesis with them. And they don't have just STEM activities, but they also have other things which are connected to space, because there is not just scientists, STEM scientists working in ESA. So for example, there is a training course on space law. Now, something about Fly a Rocket, it's a program they organize every 2 years. It's for 24 students, usually around 700 people apply for this. It has a theoretical part and a practical part. We actually learned that we've been accepted last Christmas. So the theoretical part has been taking place since then. And the launch itself, the practical part, is usually in March, but due to COVID, it got postponed all the way till October. Yeah, so it's for 24 students. Those are usually, all of them are STEM. So there were physics students, aerospace engineering, programming, electrical engineering. So all varieties of STEM students. So something about the theoretical part, they encourage group work, which is really nice because you have to learn to work together in order for the launch to work. And it's split in 2 parts with 2 deadlines. It covers topics like orbital dynamics, basic rocket calculations, and numerical rocket calculations, which we did in Python. So we had to calculate the trajectory of the rocket. And what was really nice about it was that we all got individual feedback. So they all went through all our solutions, and we were told what we need to improve, how to improve. It wasn't pass or fail, it wasn't marked or anything, but if there were points we missed, they made sure we knew about that and learned from it. So we were ready for the launch campaign, which at the time we didn't know if it was going to take place or not, because it was early start of this year and it didn't seem very optimistic. So the launch itself, the practical part, happens at Andøya. The last part of the trip, you have to take on this plane, which kind of looks like a bus. I'm just trying to get a laser pointer. Yeah, it kind of, it's sized as a bus on the inside. It's just half-hour flight for the last part of the flight. And it's very north of Norway. So you can see auroras, as we have here in the picture up there. So why is it all the way up north? So one of the reasons is that it's deserted there. There isn't many people. So if the rocket falls somewhere, it's very easy to not hit anyone. So it's safe. The only issue they have there is not trying to get into Russian airspace. So they also have to take that into account, because there have been troubles in past where they invaded Russian airspace with their rockets. And yeah, so it's really up north. And why do they launch rockets up there? Well, because they can see the auroras there. So they mainly do magnetosphere science there. It's good both visually and for sensors. So they usually launch sounding rockets. Some of them have recovery systems, which means they get the rocket back. Some of them just crash into the sea like ours did. And there's also this island or islands. It's part of Norway. It's called Svalbard. And they sometimes launch the rockets to meet up so they can measure whatever they're measuring at a time in different height levels at the same time. And these rockets are usually recovered. NASA launches there as well, because there isn't many places where you can get to North Pole. The other option is, for example, in Canada. So it's one of the really important sites, and they're expanding even more and planning to expand even more. So before the launch itself, we had to prepare a weather balloon, which again was not recovered, unfortunately, and it just crashed somewhere. It was this small box and this kind of big balloon. It expands as it gets higher and higher and higher. And thanks to that, we got the data to kind of expect what's going to happen with the rocket, what the pressure should be up there, what temperature. So for example, here we have temperature. So the black line is how it should usually look like, and the blue line how it actually looked like during the launch of the balloon. So we could compare the data later on with our rocket data, because the rocket itself was measuring as well. So then we have the rocket. So this is how the table was prepared when we arrived in the lab. There was the nose cone and the fin part, the engine part. We were split in 3 teams: telemetry, who were looking after talking with the rocket, so the radio, decoding the messages and all of that, sensors. There were 16 people, so we were making sure that the sensors work, because as you can see, we just got the circuits and we had to solder on it and make the sensors work, test them, and make sure they're where they need to be. So for example, I had optical sensor and I needed to make sure that it can actually see outside, because if it couldn't, there would be no point in optical sensor, because all the sensors were placed inside of the rocket. We'll get to that. And then there was payloads team, who were looking after the placement of the sensors as well, and making sure the rocket is balanced and all of that. So our rocket is called Mongoose 98. Don't worry if you haven't heard about it, it's not really important. But the nose, so most of the rocket is made from carbon fiber, but the nose is glass fiber, because it doesn't interfere with GPS as much as the carbon fiber. This is electronics plate, which was in the middle of the rocket. All the electronics were mounted on it. Just to get an idea, the rocket is 2.7 meters long and has about 10 centimeters in diameter. It weighs around 19 kilo when it is fully loaded up with fuel and engine. Engine is the only part we didn't get to touch because of health and safety, so that was done for us, but everything else was our work. They probably don't like students exploding. And then 10 kilo is when you don't have the fuel in there, but everything else is there. So like I said, we had to do everything from soldering the sensors to countdown. So we also had positions during the countdown. So there was usually someone from the Andoya Space Center staff and a student. So when we actually had the PA announcements that we are preparing for launch, we are at this stage of launch, it was the students doing that and Andoya staff looking after us. So here we can see this is prior to the launch, and here we are starting to get some data from the sensors. And yeah, that's us soldering. So this is the rocket model, what it looks like. And just to get an idea where the electronics board is placed, it's roughly around here. And then this whole part is just the engine and the fuel. And this is us holding the rocket, so you get an idea what it looks like compared to humans, although, yeah, compared to humans. So that's without the engine. So the engine would be slightly going out there as well. And it had a solid propellant, which means it's this kind of grain. The rocket has 2 rails on it, or 2 rail attachments, and those rail attachments go on this rail. So this is the launcher. It has this retractable roof, so the roof moved away, and then the launcher lifted and corrected its azimuth where we needed it to go. Don't worry about this part, that's for different kind of rockets. So we use this one, and then when it's just launched, it just goes up the rail and fires off. It's been corrected and stabilized, so it started spinning really fast as it went, because the fins are slightly slanted, so it makes it spin. So let's have a look at the launch itself. I think it should play now. You might hear sound, you might not, but there was a countdown, and then it just fires off, and it goes above Mach 1. So there is this kind of delay of what you see and when the sound comes in. So then we got the data from the rocket. So we wanted to compare it with the balloon data and what the models are for that area. So for example, here we were comparing magnetometer, optical sensor, and accelerometer to find out how fast it was spinning. So if we just very simply look at the graph, we can see that it started spinning really fast during the time that the engine was on. Then it was slowing down, and once it got to the top, the apogee is what it's called, it slowed down the spin, and then it started going down again. So it speeded up again a little bit, and then possibly here it crashed, or we just lost the communication. So we are assuming it crashed because the time of flight was what we expected. It went to about 9 kilometers. So and it crashed into the sea. We actually had to adjust our azimuth when we were launching because there were fishermen there. So that's probably the only issues they have there when they're launching the rockets. And then they have to obviously clear out the airspace, communicate with the airspace control, the maritime control, everyone to make sure it's safe and it's not going to hit anyone. They actually have one order of magnitude better safety than some European spaceports, for example, ones in Sweden, because they can afford that. There's not many people around there up north. So after that, we had to do the preliminary analysis of the data we got, and now we're working on the report we have to submit to ESA by the end of this month, where we're summarizing what we did and all the data we found. And we've also submitted an abstract for Symposium for Space Education Activities, which is due to happen in Barcelona in April. And we're hoping for our paper to get selected so we can get to go there and present it. If not, we still want to go there because it's really interesting networking opportunity for students like us. And yeah, here's us doing the presentation. And yeah, that's it. So if you have any questions, please feel free to ask them. I hope I wasn't speaking way too fast. I would be happy to talk about it if you want to chat privately. So there's my contact. And also I recorded a video which describes it and shows more pictures and videos from the campaign itself. So if you want to scan the QR code, you can find the videos there. And that's all from me today. Thank you. Okay, now I guess there's this silence in online events afterwards.
Yeah, there's usually a bit of a delay for questions coming in.
That's fine.
We'll wait a couple of minutes and then, yep.
Sure. I can actually, I guess I can open the Q&A here. So there is a question, how did your optical rotation sensor work? So the way it worked was the rocket had 2 holes in it, which were at, I think, 45-degree angle. And the optical sensor was a simple photodiode. So it was reacting, the resistivity was changing based on the light arriving on it. And because the sensor was closer to one of the holes, we could not only tell how fast the rocket was spinning by taking, because there was always a big peak and a small peak. So we got more light and less light. And based on that, we could determine the speed by taking the big peaks. So the peak to peak time, how fast it was rotating, the frequency of it. And since we had 2 peaks, we could see if it was a big peak and quickly after that a small peak, or if it was a small peak and a big peak. And based on it, we could also determine the direction of the rotation, which actually I don't remember now, but yeah, I hope that answers your question.
Okay, so yeah, I think that's it. Thanks very much for the great talk.
Okay.
And yeah, that'll be
Thank
it.
you. Okay, thanks everyone for watching. Thank you. Bye.